started. We are going to start about 4 minutes late. Okay, first of all, thank you for all those that they sent the answer for the homework for last 2 weeks. Thank you for those, and I like to see even more. Yeah, like the other week, 2 weeks before the exam, most of the class I can see almost everybody except one or two. They sent a lot of homework to me, and because of that, you saw the results for the exam came out much better, very good actually for the second exam, and made everybody happy. Please do the same. Please do the same. And this chapter is very important, columns, and please work on the examples, do the homework, send that to me, ask your questions. I will try to answer you uh, based on the questions that you have. And at the end, you can see the difference for sure. Today, I'm going to continue for columns that is not the same as, oh, actually, this is not the one that I want to share with you guys. Let me go with this one. I will answer to actually the chat. Please let me set this up first. That's the wrong one. Okay, so let's go to chat, and you're also why I'm doing better. Seeing you work examples help a lot. Very good. Thank you. Thank you. And very good. Thank you for all the notes that you are giving to me. Can help me to help you better. Yeah. So if I know how can I help you more, and how it helps. And just remember, like always that I mentioned, if you want to learn, you have to do most of the work. Yeah, because you have to understand this stuff. I can do just I can go so far and not more than that. Yeah, there is a limit for me to go to what stage for your learning. After that, it's just you. Even if you go 10 times after that, I can't do better than that. And the rest should be on you. And I know it's a lot of work, especially if you have few actually courses in this semester and you are working. So for sure it's harder, but doesn't matter. You're young. You can do it. Don't worry. And just find your questions, ask me. I can help for sure. I will help. Okay, let's go after this column. Just most of the time, the column has directions. Yeah, when you have, let me plot something here to make that more clear. Imagine if we have a frame. Yeah, I will try to show this better. Okay, so I will go with one story frame. Yeah, one story. So in this case, when you put load here, you will get bending moment on this column at this direction. Yeah, look at this moment at this direction around this axis. Okay, that's the moment based on this load beam. If we put load, it will bend the column like this. Yeah, like this. But most of the time, frame has two directions. So you have frame at that side. Also, you have frame here as well. So you have some load here as well. So it can bend the column other direction. So in this case, if I follow this line, we will get another moment around that axis. So you will get moment around both axes, around y and x. Yeah, so you have two moments, as you can see here. In this case, you have ex, ey is 0, so you have bending around y. You have ey, ex equals 0. Yeah, look at this, load is here. So ey is 0 because ex is equal 0 is on the x equals 0. But offset from the x direction is EY. So you have moment around x, moment around y. Yeah. So moment around y on this case, and moment around x, that's moment around y, and moment around x you will get at this side. Then your column will carry both of them together if you have both together. So you have EX and EY at the same time, like this column. You have eccentricity from X direction and Y direction. So you have two bending moments on one column. So in this case, the calculation for this is not the same, and it's very hard actually. Recently, I worked on this part, and I came with a solution to make that easier than this. Yeah, that's there are different cases how to design a column with bending moment around both axes. Yeah, these are two of those methods. So I'm working on it, and I came up with solution. Hopefully, if I can find time, sometime, I'm going to put them together and actually send that to ACI for publication in ACI journal. And also in future, if we can actually use that in different another method here for columns with moment around both axes. So it's very interesting stuff, and it's not that easy stuff as well. But this method made that easy. So I'm going to teach you reciprocal load method, and hopefully you can see it's not that hard. Just you have to follow the instructions step by step and find the moment. And as I mentioned, if you have moment around, for example, x direction, that's the curve that you can plot. That's your CB, less than CB in tension, more than CB in compression. If you have moment just around y direction, that's your actually diagram. That's your CB. C less than CB, C more than CB. So you can see these two diagrams based on the things that we know. Today we are going to learn if you have both of them together. So in this case, we have to connect these two on this M and My actually playing together. And then this curve will rotate all the way to reach to the other part. So these two are not similar. So those are not similar. As you can see, this length is not equal to that one. This length, no, because you have different moment. M and X is not equal M and Y. So those are not equal. So when you have EX and EY, then you have to find some point here. Then go all the way parallel to P. And if that point, look at this, one point here, if you go here, yeah, and go to that way, you can find that's your PN for this column, or PU. Then go vertical and just perpendicular to My and Mx. That's your Pu, Mux, Muy. Those are based on the loading. If it's inside or on this curve, then that column with that rebar is acceptable. If this point instead of here is outside of this, so in this case it's not acceptable. You have to change the size of the column or use more rebar. Yeah, and the percentage should be 4% if you're not using couplers. Yeah, so we went through this stuff. Just I'm refreshing your memory to go after this part. As you can see, this is very interesting that we know this right now. We know that one separately. If we add them together, how can we calculate this? And how can we find this? Actually, when I was a student, I completed my almost close to the end of the BS, I started working in a company, and I was very interested to find this solution. How can I find this curve to check this with this point, if it's inside this curve, on this curve, or outside? So I tried hard. It was a long time ago that we didn't have that access like today to the internet. So I have to do the search just find somebody to answer me, and some professors that they work on this in ACI. So I try to find them, and finally, after about I think 6 or 8 months, I wrote a program with Fortran 4 at that time that could solve this problem. So that's perfect. When I did that, I was very happy. I could actually do that. So it's very hard. It's not using this method. No, that's a real method. This is just simplified method. It has some limits. If you are not in that limit, the answer from this method is not acceptable. Just remember, these are just simplified method. It's not the perfect or final method. But there are some cases that you can do it, like plotting this and then find this curve and then check if your point is inside, on, or outside. That's the system that will work with no limits. So if you are you like to do that, please let me know. I'll you working on that. It will take time, but at the end, it's very sweet to solve that problem. Okay, let's see how can we solve this problem based on that reciprocal load method. Okay, that's the equation. We have to just find this and based on this, find Pn and compare that with load from outside. So these are based on the capacity, based on the material. Okay, how can what's this part? Pn is approximate value of nominal load in biaxial bending that the column with that rebar arrangement and the size of the column can carry. So that's the final load, that the nominal load that this beam can carry. Yeah, this is provided. So phi Pn will give us Pu provided, and we can compare that with Pu coming from the load. If it's more than that, we are good. If it's less than that, no good. Okay. What are this one? Pnx0. Just remember, as soon as you see this zero for Pnx, means Ex is equal 0. Look at this. Ex. Just it's not too hard. X0, EX0, Y0, EY0. When EX0 means that we have eccentricity around Y, because EY is not 0. Yeah, look at this. EY is not 0. So let me show this again here. In this case, your EX is equal 0. Look at this. From here, perpendicular to X, your EX is 0. But EY, you can see from here to there is your EY. So whenever EX is equal 0, but you have EY, means that you have moment around X. So Pn times EY will give you moment around X. You can see this one will rotate around X. So EY, moment around X. EX, moment around Y. Just remember. In this case, EY is equal 0, you have EX, means that MY. EX, MY. EY, MX. Yeah, not that hard to actually accept this one. So what was the rule? E for this one, X0, EX equals 0 means we have EY. So in that case, you have M around Y. M around X when you have EY. EY, M around X. PNY0 means Y, EY equals 0. We have EX because EX is not 0. So you will get moment around Y. So nominal load when only eccentricity EX is present. Yeah, EY is equal to 0. This one, nominal load means that axial load, that when you have EY only and EX is equal to 0. So these are the definition. So we have to find this, we have to find this, and then find nominal load for concentrically load column. It means that no EX, no EY. How can we calculate that? ASFY, ASTFY plus 0.85 F prime C times B times total B times D minus AST. You can remember that that's the start of the column that we learned. So with no eccentricity, this is a P0. Today, I'm going to solve example, and you can see how we can find all these stuff. And it's a kind of review for whatever we learned so far from ACI method. Okay, and what is there? So you can find P0. You can find PNY0. Yeah, you can find PNX0, put them in this equation, find that, and then inverse of that, you will find Pn. That's your Pn. And compare that with phi Pn means Pu provided, compare that with Pu from loading, and that's it. If it's greater than, okay, not greater, not good, and we have to change something. And what is the limits on this? The limits is your Pn, when you calculated Pn, must be greater than or equal 10% of P0, means with no eccentricity. We calculated it already. After you calculated Pn, you have to compare that with 10% of this. If it's greater than 10%, this equation will work. If it's less than that, it's not that accurate answer. So you have some answer, but it's not that accurate. So it's not that good. Another limit, phi Pn, find this Pn, and then phi Pn means Pu. Yeah, that's Pu provided. Must be less than or equal 0.8% phi times P0. So again, phi times P0 times 0.8. This phi Pn must be less than or equal. If it was greater than, is still the answer that we got is not accurate for that problem. So these are the limit. If you're out of the limit, this system, this method is not working well. If you are within this limit, yes, that's good to use. Okay. If you have any question, please stop me and ask your question. If you're not asking question, I think you can follow me and you have no question. Yeah. Like always, stop me if you have questions. Okay, I don't know why I have this twice, but it doesn't matter. Okay, okay, let me answer one chat. Is phi equal 0.65? That's correct. That's for the column. Always very good question. Yes, it's all for the column. And I will talk about this in example as well, but good point. Yes. Okay, imagine we have a column like this. With this rebar, actually, we have 8 number 9. Did all the distances. We know the size of the column. This is, so which one is B, which one is H? Because we have eccentricity from both sides. No, we don't know which one is H, which one is B. So in this case, we don't know. But because we have to find Pnx0, Pny0, it means that eccentricity around one axis only. In that case, we know which one is B, which one is H. So right now, there is no difference between B and H for us. Just we know the dimensions. Okay. We know the total Pu from loading is 255. This Pu is 255. We know the eccentricity 3 and EY 3 inches and EX 6 inches. As you can see, EX from here to here will create moment around Y, MY, EX, MY, EY, MX. I hope it's completely clear. You have 3 inches, so it will rotate around X. So EY. You have EX will rotate around Y. Okay, so we have this eccentricity. How can we calculate this from the moment distribution for the frame? At first, we have to analyze a frame. You have 10 stories frame. Do the analysis. Look at this. Let me make that one more time clear, because these are the bases. If we don't know the bases, all this knowledge is not that useful, because we don't know why we are doing that and how we can get those numbers. And those are important for you guys in future and for all the tests that you have to pass in future for your EIT or PE or higher than that for your SE. Okay, so imagine we have a frame, so many stories, and we are going to design this column. Yeah, we are working on this column only. And because this frame has another frame perpendicular to this, I didn't show that. So you have two eccentricities. Yeah. So you will get two moments, mx, my. So at the end, you have mux after you analyze this frame and that frame together, 3D analysis for the frame. Yeah. So for this column, you will calculate mux, muy, yeah, and pu. But remember, when you calculate this stuff, you have one mx on top, one mx at the bottom. You have, because it has two ends, yeah, and A and B. You will get M around X at this point, M around X at this point, M around Y at that point, M around Y at. So you have 2my, 2mx. Why we have two over here? These are the maximum. Yeah, when we are talking about short columns, like this, the buckling is not that important. How can we make sure it's short column or long column? We will learn later. Don't worry about that part. Just learn this stuff first. So whenever it's a short column, you will go with the maximums. You have four moments, 2mux, one top, one bottom, 2mu1, one top, one bottom. And then you pick the maximum mu for x, maximum mu for y. So you have one mux, one. How can I find ey? So moment around x will give us ey. So ey, I can write ey is equal mux. Just remember this or write that down for yourself somewhere. Mux divided by pu. That, so we got that actually ey from this equation. We analyze the frame 3D. We find mu maximum x, mu maximum y, and pu. Then ey is mux divided by pu. Ex is equal pu divided muy divided by pu for ex. So ex equal muy divided by pu. That's it. Yeah. How we calculate this? That's the method. We calculated ex and ey plus the total load pu. And with this rebar arrangement and the size of the column, and with the f prime c and fy that we consider f prime c and fy, we want to make sure that this column can carry this load or not. Okay, I hope it's clear. If it's not, please let me know. I will go through this one more time. Is that clear? If you're not answering, it means that yes. If you have question, before I remove this actually stuff, let me know. Any
Professor,
question on this?
Professor, why are there two MUK and MUX and MUY?
Uh, please ask your question one more time.
I see the frame has three level, but then why we only have two MUX and two MUY?
Look at this. It has 1, 2, 3, 4, or it can be even more, 10 levels. Doesn't matter. I'm talking about just this column. Look at this. I'm designing one at a time, just this. Then you have to design this column, that column. All the columns you must be designed. Right now, I'm designing A, B, A, B, just this column as an example. Yeah. Okay, for this B, as you can see, we have bending at this side, we have bending at other side as well. So we have bending moment around X and Y because we have 3D frames. So it will carry bending around X and Y. So you have MUX at A, MUX at B. You have MUY at A, MUY at B. 2MUY, 2MUX. Then we pick maximum of those two. Doesn't matter the absolute value. Remember, if one of them is negative, don't worry about the negative or positive. Go with the direction, but consider absolute value of that and compare that. Negative 150. Which one is greater? Negative 100. Absolute value must be greater. Yeah. So these two are the maximum of the moment at A and B for both directions. Did I give you the answer?
Somewhat. Thank you, Professor.
Okay, very good. So is there any more question? Okay,
Hang on. So for
yes.
this one, we just solve for MUX and MUY with the equations that you wrote down.
That's correct, because those are the maximum moments. We are not, if the this column can carry PU with MU max and MU max, for sure it can carry PU with MU mean, because the moment is less. So for sure, this column can carry the minimum when it can carry the maximum. Clear?
Yeah.
Okay, very
It
good.
doesn't seem too hard.
Yeah, I think it's not that hard. Just follow the instruction. When it's not that hard, it means that you started reviewing. You did review. Yeah. If you are not reviewing and you are not just doing whatever you should do, so it should be hard anytime. But it's very good. I can hear that it's not that hard. Perfect. I like to hear this. Okay.
So, but then why do we need F prime C, Fy, and 8 number 9 bars in AST if we don't really need that to solve for MUX and MUY?
Look at this. Those are based on the loading. I have to find the capacity,
Okay.
then compare the capacity with the loading. Yeah,
Okay.
these are based on the loading. Then we are using size of the column and the rebar. Then we have to find the capacity. The capacity must be greater than or equal the load from outside. Clear?
Yeah.
Perfect. So because of that, these are loading. Then we have to find the capacity based on the material. Compare this with that to see if the column can carry the load or not. Okay, let's go and see what can we do. Step by step, we know that equation 1 over P n, yeah, we have to find all these parts. Right now, we have to find this part, and this part. Pnx0, Pny0, P0. Then put this in this equation, find Pn. This Pn is your capacity. Then phi Pn will give us Pu capacity, and we can compare that with this Pu. That's it. If it's greater than or equal, we are good. Okay, so a step by step, we have to follow that instruction. First of all, if we go with this direction, means that if we go H here, look at this, H at this side, H at this side, means that we have EX, EX. So in this case, EY is 0. Yeah, bending about Y axis means that we have EX. EX is 6 inches. Okay, so we have moment around Y. In this case, H is parallel to E. Look at this. So that's your H. This is your B, because we have moment around one axis. So B and H is important to be able to use the ACI. If we are not using ACI actually method, B and H doesn't matter. You can go with H here, B there. Just those are names. But because we have this gamma is equal H minus cover divided by H. So in this case, we should know what H means for ACI. H parallel to E. Okay. In this case, we have EX. So H is this one. H minus 2 cover means 20 minus 2.5. Minus 2.5 cover means to the center. This cover to the center. We'll get 15. 15 divided by H, 0.75. Okay. So that's the equation again. I wrote that, but we know that already. Then we know E over H. Yeah, H is 20 inches. E, we know EX because we are working on EX right now, EX only. And rho G is AST, total AS, means 8 times cross-sectional of this number 9. Total is 8 square inches. 8 divided by total area B times H. B times H. We will get 0.003. As you can see, we do not have 0.75. We have gamma for 0.8. We have gamma 0.5, 0.6, 0.7, 0.8, something like that. We don't have anything between 7 and 8. So in this case, we have to interpolate. And because of that, I wrote this here, how to interpolate. Just refresh your memory. Interpolation should be from the high school. It's not that hard to actually remember. But still, I show that here one more time to calculate that. So at first, we need A6 and A7. As you can see, equal rebar at either side. Why we need equal? Because we have moment around both directions. If we have moment around one direction, it's better to have rebar just at one direction. Those directions should be parallel to E. So if you have MY only, just rebar here, rebar there is the best. You don't need to install rebar middle. It's not carrying that much load. But when you have EX and EY, so you need at 4 sides. So that's the best rebar arrangement when you have rebar moment at both directions. Perfect. So A6 and A7, let me go to those to refresh your memory again. That's your A6. As you can see, F prime C 4, Fy 60, gamma 0.7. But we need 0.8, but 0.75, but we don't have that. We have another one, 460.8. So we have to use this one and that one. Then based on these results, find for 75. We can calculate for 0.7, 0.8, and then for 75, we have to interpolate. That's why I wrote this here like this one from graph A6 and A7. Okay, from graph A6, based on E over H and rho G, let's go to that one, 0.33 and 0.3, 0.033 and 0.3, A6, that's or A6. EH is 0.3. Okay, we have 1, we have 0.5, 0.4, 0.3. Yeah, so E over H is 0.3. That's the line. And we have percentage 0.033. 0.03 means 3%, and this is 0.3. So 33, this is 0.3, 0.4, 0.35, 0.3, somewhere around here. Yeah, imagine this is the point. From here, just make a line and read this number, 0.60 something. Yeah, that's the number that we can read from A6. Let's back here. From A6 at Kn is equal Pn divided by F prime CAG 0.65. One more time, let me show that to you to make sure that we got it correctly. So E over H 0.3, that's it. That's the E over H. You can see this is E over H, all these lines. E over H 0.3. Percentage of liver 0.333 means 3.3%. This is 0.3. This one is 0.3. 0.033 should be somewhere around here. At the middle, 0.035, 0.04, 0.035, 0.003. If we go this way, they read this number 0.65. And as you can see, this is your Kn, and Kn is Pn divided by F prime CAG. Yeah, or you can write that based on Pu, doesn't matter. So we went with this Kn, we read that 0.65, Kn 0.65, and it's Pn F prime CAG. Okay, 0.65, Pn. Why I wrote that Pn X0? Because right now we are considering that over here. We considering that 0.62, that's the Kn. I show that the other one. Please just forget about that section. Yeah, the same number, but I read that number from 0.03, and 0.003 means these two. I read 0.62. Okay, that's for gamma is 0.7, and that's your Kn. Yeah, Kn is Pn divided by F prime C Ag. Perfect. And this Pn, as you can see, is when Ey is equal 0. So we call that Pny0. Over here, we show that Pn, but this is our Pny0. Yeah, that's it. Because as you can see, Ey is equal 0, so we call that Pny0. If we put this Pu over here, the Ex equals 0, then we call this Ppnx0, because Ex0 over here, Ey0, Pny0. Yeah. So those are the definition. Then this is for 0.7, but I want for 0.75. What should I do? I have to go to A7, do that again for 0.8, gamma 0.8. Yeah. And I went there with these two numbers, 0.3 and 0.003. I went to other one, again to A7. Yeah. Again, 0.3, 0.003. Yeah. Somewhere around here. Go this way and read that number. That's it. Do the same for A6 and A7. Okay. We did that and we read that Kn 0.66. Perfect. Then 0.75. How can I do? That's the method. I wrote that for you. If you know other way, just do it your way. Yeah, just make sure that you are getting the same answer. That's it. Okay. I started with this side. Look at this. When I started with this, always I have to start with it. If you start with that side, doesn't matter. You can write 0.7 minus 0.8. But keep this always for all four sides. This one first, that one second, this one. But I started with this one first, bigger number. So 0.8 minus 0.7 means 0.1. Always do the same. This side minus that side. Okay. And the answer for Kn again, because I started with this Kn minus, so delta gamma, delta Kn. Delta gamma is 0.1, 0.8 minus 0.7. Delta Kn, 0.66 minus 0.62. That's it. Then go with, if I want to find this one, again, go with this minus this, because always start it. So for 0.8 minus 0.75 means this difference. The Kn should be Kn for 0.8 minus Kn for 0.75. Look at this. That's it. That's the determinant you can write. This one minus this one, delta gamma is equal delta Kn, this one minus this one. And for here, for the one that you want, delta gamma should be 0.8 minus this. Delta Kn should be this one minus Kn for that we don't know. Yeah, Kn for 0.8 minus Kn for 0.75. Yeah, Kn we know Kn for 0.8. For Kn for 75 we don't know. How can we calculate this? 0.1 times this is equal 0.04 times that. I wrote that here, 0.1 times total of this equal 0.05 times 0.04. That's it. We know this point Kn point, then that side divided by 0.1, you will get this number Kn 0.8 minus Kn 0.75, 0.02. Then I know this Kn for 0.8 is 0.66. So I will write 0.6. I can calculate Kn 0.75 is equal. You just move this to the other side, you will get Kn for 75 is 0.64. That's it. Yeah. So that's interpolation. If it was 0.73, 0.72, 0.79, whatever, just do the same and calculate. Just this number must be between those two graphs that you picked. That's the only thing that you have to follow. Then based on this, you can find your Kn that you want. Then I know Kn is Pn divided by F prime C. And Pn for this case, because Ey is equal 0, we call that Pny 0. Look at this. We have Ex, Ey is 0. So Pny 0 equal 0.64. F prime C we know 4. Ag is 12 times 20. 240 AG. You can calculate PNYO. That's a Y0. That's it. If you got it, you got the PNX as well. So in this case, we have eccentricity at Y, EY, and EX0. So we call this PNX0 because EX is equal 0. So in this case, gamma is, as you can see, which one is your H? H is this side, parallel to E. As you can see, I wrote that this is your new H, parallel to E for ACI charts. So means H minus the cover means 12 minus 5 is 7, as you can see, divided by H, 12. 58. 58 is not number that we have. In this example in the book, just they consider, okay, 58 is very close to 0.6. So we consider 0.6, and they didn't use the interpolation. But for you, please, if you got something like this, go with interpolation based on that. What chart should I use for 0.8? 0.6 and 0.5 and 0.6 for this one. Yeah, because 0.58 is between 0.5 and 0.6. So I need to have the two charts, 0.5 and 0.6. As you can see, I have 0.5. 4 equal sides, rebar 4 sides equal, all of them, A5, A6, A7. That's important. You shouldn't go to one that has rebar at 2 sides only. No. So in this case, if I want to solve this, I will go with 0.5 and 0.6. Do the same as this one. Yeah? Just follow this instruction. Go A5 for 0.5, A6 for 0.6, and follow this instruction. And then for gamma equal 0.57, 58, find that gamma. And based on that Kn, for that Kn, that's it, you are done. Over here, they made that easy and they consider, okay, it's very close to 0.6, we will go with 0.6. Yeah, but please, you shouldn't do that at first or after you got experience. If after a few years experience, you can see the difference is not that big, so you can go with this. But until then, please follow this instruction. Go and find the numbers between those two charts. That's it. So in this case, because we went with A5, yeah, actually, we went now, I think I wrote that wrong. I should write this point A6 because A5 is, yeah, no, that's correct, 4.6. That's correct. Yeah. So we went that with 0.6, not for between 0.5 and 0.6. So they use a graphite. Okay. For grad A5, do the same. Eccentricity divided by H. We have 3-inch eccentricity divided by H. In this case, is 12 inches. Yeah, 25. Rho G, total AS, the same as before. It's not changing. And go to gamma 0.6 and read Kn. So in this case, if we accept this, that is 0.6, there is no need to calculate Kn. Just read that from the chart. So with that 0.003 and 0.25. So in this case, 0.25, you can see 0.20, 30, 25 is at the middle. This is EH equal to 0.25. Yeah. And then I tried to show that 0.20, the percentage, 0.33. Look at this. Over here, I show that this is consider I couldn't plot a graph like this. So imagine this is the correct, especially at this point. So that's 0.33. This is 0.3, 0.33, 0.4. Then go from here and read this number. That's your Kn. Okay, we did that. Based on this Kn, we got 0.65. Okay, 0.65, we know that this is Pnx0 because Ex is equal 0. We have Ey. So Ex is equal. So we calculate Pnx. Then how can we calculate P0? That's the easiest equation that we know from the start of the column. AST times Fy plus 85 F prime C times Ag minus AST. Sometimes we consider this, sometimes we say, okay, it's not that important. But if you want to do the best, always consider this. Yeah. until you got that experience that for very big size column with a small rebar, you can neglect that. It's not that big difference between considering or not considering that. Until then, just consider. So in this case, we calculated P0. So we calculated P0, PNX0, PNY0. Put them in this equation. Plug in, yeah, 1266, 68, I think. I'm not sure. I think it should be 58. The, forget, yeah, I think one of these two is not correct. Yeah, I think maybe this is not correct. 1258, not 68. It's not that important. So put that number here. Then PNY0 from other page 614. PNX0 625. Put this in this equation, you will get this. Inverse this, you can find PN. So your PN, that this column with this rebar arrangement and F prime C and Fy should be 400K when it has two eccentricity, because we consider that, yeah. When you have eccentric X and EY, this column can carry PN equal 410. That's it. Then we have to compare that with PU from loading. Okay, how can I compare that? Before that, I have to check if it's acceptable or not. What are those checks? Those checks is, one of them is PN must be greater than or equal 10% of P0. Okay, 10% of that means almost 127. 10% of that, yeah, means 127. Just rounded. So this one should be greater than or equal. That's good. So we are good. Again, another limit. PN must be less than or equal 80% of this must be less than that. 80% of that, you will get 10, 15. 410 is less than that. That's good too. And as you can see, PN. Just we didn't change anything. Everything PN. Then find the capacity. PU capacity should be phi times PN. The final PN that we calculated for this, phi times that is PU capacity. Then compare this with the loading that we had from the outside. As you can remember, this load was 250 PU. Yeah, that's coming from the actually analysis of frame analysis. We got that 255. So our PU that this column can carry, we consider 267. It is greater than 255. So we are good. So the column is good and it can carry the load. So any questions so far?
Yes. Just to make sure, P0 is the tension, right, Professor?
No, it's compression. Everything here is compression. No, is axial load without any moment. Axial load without any moment. So it is that pure axial load. This column can carry this much of pure axial load when it's short. It can't buckle. Yeah. So that's your P0. Clear?
Yes, sir.
Okay. Any other question?
Yes. To get Kn in the graph, we see E over H and rho G.
That's correct.
Where they meet is the Kn.
No, where they meet, look at this. That's your rho. Yeah, you got 3.3 means 0.033. It's
Yeah.
here. And E over H is 0.25. Over here, when they meet, from here, make a horizontal line and read Kn. This line is Kn. That's correct. From here, go this line. And you can go, just remember, you can ask why you should always you go vertical, horizontal. Why you shouldn't go downward? You can go downward as well. You can find Rn. But in Rn, you can see Pn times E. We have one E. We have to do extra work here and then find H. So that one has less parameters. And because of that, we read Kn.
Okay.
Clear?
Yep.
Perfect. Any other question? Don't worry if your question is too easy. You think, oh, I'm not sure, I'm shy maybe I'm asking wrong question. Doesn't matter. Even if your question is completely wrong or something that you should know, I'm not to tell you, oh, why you don't know this. No, I'm not. I will give you the answer. Yeah, please ask your question to make that clear before the end of this lecture. Then tonight you can start imagining about this and try to review it with yourself. That's the way you can learn this faster. Okay, what's the question?
So Kn is like, is it like a reduction factor or?
No. Those are two factors. This Rn has to do with eccentricity means moment. Pn times E means moment. This based on the moment on the column. This is based on the axial load on the column. Those are two factors. That's it.
Okay.
Yep. Okay. Any other question? Okay. Doesn't matter if we even pass and then you remember a question, you can ask, and I will back to this again. And this is your homework. As you can see, do the same. I gave you MUX means MU max. You had two MUX to pick the maximum, and these are the results. Yeah. And with one PU. Okay. And you have EY and EX. I gave you EY and EX. I think I should have somewhere this too. Okay. Look at this. I didn't give you EX and EY. Can you solve this problem?
Yes.
How?
You divide PU by MUX.
MUX
And
divided by PU, we give you EY.
yes.
MUY divided by PU, we give you EX. Very good. Very good. Yes. So I can give you EX or an EY, or I can give you MUX and MU. Just remember, MUX divided by PU will give you EY. Remember, otherwise everything is wrong, because you will go with different edges perpendicular. So if you consider that EY, you will get different numbers. So MUX, look at this, when you have EY, so you have moment round X. So moment round X divided by PU will give you EY. Moment round Y divided by PU will give you EX. That's it. So you have EX and EY. Then solve this problem exactly the same, and just do not assume 0.58 equal 0.6. Just go and find the information actually practice. Okay. I think you are one of the good classes so far that you got this very fast, because I can remember for other classes, I spent more time to explain that, and they still had some struggling understanding those stuff. But I think you got it, and that's very good. But please do practice right after this, because right now is in your short memory. Tomorrow you will lose some part of that. Then 2 days after that, 50% is not in your mind. So you will lose 50%. 3 days, 70%. So do it tonight, review it, and try to keep in your mind and make it ready for tomorrow to solve the example and then the homework. Okay, we are done with short column. Short column is very easy, yeah, because you have no concern if it can buckle or not. But for slender column, it might buckle. What's the difference between these two? Look at this. That's very important concept from strength of material. Uh, Imagine I have a column or piece of wood or whatever, yeah, that, and I will put force on top on this one. It means that I have the same load at this side, yeah. because when you push it, you will get the same force at the bottom side. And because of that, it's a stable. Sigma Fy equals 0. Otherwise, it's not stable. Okay. So if the column can reach to Fy, imagine this is just one material. So in this case, Ag times Fy, yeah, is the total load that this column can carry. This is your Pu, Pu, yeah, this is your Pu. Okay, so if you can go all the way to Ag cross section of this, whatever it is, 10 inch by 10 inches or whatever, times Fy for the material, then you will get Pu. If you put this Pu and reach to that Pu, then it start failing. It means that this column is short. It didn't buckle. Yeah, because of that, you could reach to Fy. But imagine if you have a column like this and then put load here. So before you reach to Fy, it will buckle. So the total load that this one carry should be load before buckling. It means that Ag times 1Fc or whatever, that's your new P. It's not Pu anymore. Or you can consider that whatever you want, Pu or whatever. That's the capacity for this. And Fc for sure is less than Fi. So you can see you have the same material, the same size of the material, Ag and Ag. But this load is much smaller than this load. Why? Because we cannot use the whole material in this case because it's long. It can buckle. So the buckling will reduce the capacity of this column. So it's very important to understand if the column is slender or short column or long column. Slender means long column. Yeah, it can buckle. So that's the difference between these two. The material and everything can be the same, but because of the length of that column, the load is much less than the other one. Because before it reached to Fi, it will buckle. So you can add more load because it buckled already. So the load can be before that buckling. So we call that P. Is that completely clear?
Yeah.
Okay,
Yeah.
perfect. So this is the concept that is a little higher than BS degree, but I will uh, talk about this to let you know that it's part of your knowledge from now. And you can use that in higher degrees as well, or in any firm that you are going to design or go to the actually work. So imagine you have a frame. That's a plan view of the structure. These dots are columns, the others are beams. So you have a 3D frame. Sometimes we have shear walls. Look at this, I showed them. What's the shear wall? Concrete from this column to that column with the rebar. It makes this very stiff. Yeah, we call that shear wall. How to design them? That's for graduate studies. We learn how to design those. Okay. Sometimes there is no shear walls, just the frame will work on that one. So the lateral load will be tolerated by the frame. The lateral load by combination of the frame and shear wall. So we have both cases. And then from the other side as well, I just showed it at one direction. Then for the other side, you might add another shear wall for here or nothing for this one. Yeah. So no shear wall with shear wall. Shear wall will actually create some support for the structure, and it can remove sometimes the buckling of the columns, the shear wall. That's the help, big help. So you can use a smaller column with more capacity. So why we are using this? To minimize the deformation of the structure. How? imagine you have a frame again. Yeah, that's your frame. So this is your frame. Yeah. So I show just 3-story frame. So if no shear wall here, when you have lateral load like wind or earthquake, we are not considering both loads together, wind or earthquake. So then you can find deflection here. Yeah, that's the deflection of the last column. It's supposed to go here. Just I couldn't show that correctly. So that's the deflection of this frame. That's delta. Yeah. Okay. So when you get this delta, so it means that it can buckle easier because you have huge displacement. So, but if you fill this with concrete, reinforced concrete, like shear wall, like this, look at this, shear wall from top. So you will reduce this deflection. Yeah. If this one within a range that we will learn tonight, so we can consider that as a braced frame. When it's braced frame, your length, you can consider your columns as a short column. If it's a braced frame. If it's not braced frame, it's not a short column. It might be a long column. Yeah, for braced frame, for sure it's a short column. Okay, how can we find that if we put any shear wall, is that acceptable? No. Sometimes you have huge plan and you don't have enough room for shear wall, because shear wall, you will close any connection here. And most of the time, the architect will not allow us to cover this. Otherwise, we are considering a lot of shear walls. Yeah, but sometimes they ask, no, 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 no. Outside, I have windows everywhere. You are not allowed to put any shear wall. Inside, I have open areas. There is no room for the shear wall. Then we locked. So you have to design your system like this one with no shear wall. And sometimes just you have a small piece. They ask you, okay, from here to here you can use shear wall. From here to here you can use shear wall. So are they good enough? Sometimes no. How can we check that? The method that I'm going to teach you tonight. How to check if the shear wall can be considered as braced or not. Sometimes even the frame is good enough for braced. When the columns are big, the spans are small, sometimes just frame with no shear wall, you can consider that as a braced frame and consider all the columns are short. So that's a huge, actually, things that you as an engineer, you should know. And this is for graduate studies, but I added just this equation to your stuff to actually learn, because it's very important and interesting. Frame with no shear wall can be considered as uh, braced frame, or frame with shear wall can be considered as unbraced or non-braced frame. Yeah, either one can be seen in your structure. Okay, definitions that you need to know before attacking this system. Okay, distance from bottom of the beam to top of the slab means structure. Slab is reinforced concrete, yeah, covering the floors, and the beam is horizontal elements between the columns. So from bottom of the beam to top of the slab, we call that LU, yeah, LU. From center to center of the beams, we call that LC. So LU, unbraced length. Unbraced, as you can see, the column has no support. We call that unbraced length of the column. And LC is center to center of the beam. So you can see that LC and LU with beam and column. Okay. Then just remember these two. We are going to use them in this equation. Then use this equation. We call that stability index. Q is stability index. Calculate sigma PU, calculate deformation, calculate shear for that story, and LC center to center of the beams. Just remember. Then those parts, how can we calculate those? Not that hard, don't worry. I draw something for you guys that you can actually see those easily. Look at this. Imagine you have a frame, just one span, make that simple. You have 2 columns, you might have 10 columns at each story. Then I want to check stability index for this second story. You have to go story by story. Remember, you cannot say the whole frame is acceptable for if you check all the stories, then you can mention that. But it might be actually on non-braced here and braced on top, or non-braced braced on top, braced at the bottom. So we should go story by story. Even 3D doesn't matter. I show that 2D, but if you have 3Ds, so do the same. What is sigma PU? Sigma PU, add all the forces on the columns for the loading that you have. Look at this. I show that with lateral load plus vertical load for the gravity. So find the loading based on the frame analysis. Then if you have 10 columns in that story for 3Ds, add them all together, PU1, PU2, PU3, all the way, that's your sigma PU for that story. As you can see, I didn't show PU for the bottom. No, everything for that story. Then I have to do that for this story as well. Okay, what's delta zero? Delta zero is your drift. What's the drift? Drift is equal difference between deflection of the story relative to a story below. So if I'm working on this one, drift is displacement of this point relative to the same point at the one story below. That's your drift. Displacement for top one is from here to here. Displacement for this one is from here to here. Difference between these two is your drift. That's it. What's the drift for the first story from here, here? Here, there is no movement because it's space. So this one is the displacement of the first story and your drift. For the top story, difference between that story and one story below. If we have one story on top, so this one with below, not on top. Then for top one, that one minus this one. You can find drift for the third story. So as you can see, it's not that hard. So that's your drift, delta zero. What's VU? That's the shear on that bottom of the columns on that story. Add shear for this column, shear for that column. All the columns here, when you do the analysis, you have all the shear force, axial load, and bending moment. Add all the shear force at this direction, not perpendicular, because we are checking at this direction, especially when you have 3Ds. All the shears parallel to the force outside. Add them all together. Yeah, that's your VUS. That's the total shear on that level, VUS. That's it. And how can calculate that? That's another system that you can calculate. Your VU can be total force above, or you can do that from analysis. I will go with analysis. Or if you want, you can go with this. VU is VU1 is equal F1. Total force above. It was 3 stories building. You have F1, F2, F3. So the shear on this one was F1 plus F2. The shear over here was F1 plus F2 plus F3. Over here, this VU is F1 because all the horizontal force above. The second story, all the horizontal force above means F2 plus F1. So for two, if you have 10 stories, add them all for here. Minus this one for this one. Just everything above, add them together. That's your total shear on that story. Remember, this force must be at ultimate level. So for the earthquake is strength method always is at ultimate level. For the wind, if you are using old code, that old code will give us AST method. Then you have to multiply by 1.6 to find that load based on. You will learn on, I don't know what course. We don't have any course for that, but maybe there are some course for earthquake engineering. Maybe you can learn that one for sure. So you have all the information here. You can find this. Yeah, LC center to center of the beams. Okay, for data story. Find Q. That's a number. Compare that with 0.005. If it's less than or equal, you can consider that story as braced. So all the columns and data story, you can consider them short column. If it's more than that, so in that case, you should consider that a non-braced column. It's not braced, it's non-braced. So braced and non-braced. Sorry about that. I mentioned you can consider that short columns. No, sorry about that one. You can consider that as non-braced columns or braced columns. So it will give us different K factors, as you can see on this chart. Look at this. These are the K factors. For sure, you saw that in strength of material. A lot of this stuff, you saw that. And always you see something K equal to. I'm not sure if you pay attention to those or not. What does it mean? It means that when you are in this case, the K, the length of the column for buckling will be double. So you can put less. Where the length is smaller than a real length, so you can put more load. Yeah. So braced and unbraced will give us this K factor. So in this case, we can call that braced column or non-braced column. So if your Q is less than or equal, braced column. So you can use K factor less than or equal 1. If your Q is greater than 0.05, it's called non-braced column. So you can go with K greater than 1, so you can use less load. The slenderness is more critical when it's non-braced. For braced, is not that critical as non-braced. So even if you have shear wall and your Q is greater than this, even with shear wall, you should consider that non-braced if your Q is this. So if the shear walls are small, you do not have enough room to, so your drift should be big. And because of that, your Q can be more than 0.5. So in that case, actually non-braced system, you will get bigger K factor. I hope I gave you all the information that you can see. I wanted to give you. And at the end, you can see when Q is 0.05, your moment will increase 5%. So as you can see with this system. And because of that, you can go with actually a non-braced system or brace system if it's greater than this. Yes, what's the question?
Can you repeat? You said is it if Q is less than or equal to 0.05, is it braced or unbraced?
If it's less than this, braced.
Okay.
Braced. If it's greater than this, non-braced. Even if you have shear wall. We think when we add shear wall, because shear wall or bracing is for bracing the frame. So we call that brace system, but it's not good enough. We have to check this. If it's less than or equal 0.5, it's braced frame. Otherwise, for the column is not braced frame. Yeah. So yes, what's the question?
So you said if Q was greater than 0.05, it would be a longer column, correct?
No, your K factor should be bigger. You have the same columns, but effective length of the column, because of that, I showed this slide here. Look at this. You have the same column length. This is the same as this, the same as this. But K factor for each one are different. If you have the case like this, K factor is double. It means that you have L, but the column will act like a 2L column. So it can't carry that much load. Will act with L, if you have this case situation, rolling, fixed, and fixed. If you have a connection between a frame like us, so you will get a k that you have to calculate that k between greater than 1. So in this case, less than 1, like a brace frame. You can see effective length of the column is smaller than a real length. Yeah. So if your q is less than this, your k factor means length factor of the column is less than or equal 1. If it's more than this, your k factor is greater than 1. Is that clear?
Yes. So then in that case, we would not put bracings for that.
No, you might have bracing, but even with bracing, if those bracing is not good enough, is not big enough, so still you should consider your columns as non-braced columns.
Okay. Thank you.
Clear?
Professor, so which K will the column be more rigid, more stable?
I can understand your question. Which K?
In which case, Q smaller or less than 0.05 or Q?
Yes, yeah. When look at this, that's the stability index. When your Q is smaller than this, it's a braced column or braced frame. If it's more than this, non-braced.
So for the brace, does it mean that it's more stable?
It's the movement is less, more stable. Yes.
Thank you.
Yeah. Welcome. Any
If it
other
was
question
brace-
on this?
If it was brace, Professor, would that cause it to not buckle?
Actually, the movement is less. So the P delta effect is less. It's not just buckling. Look at this. So for brace frame, another system that you have. Imagine if you have a frame like this. And these are very good questions. If we have load on this frame, yeah. So, and you have this lateral load. So this lateral load plus this will give us a P load on top of this column. Yeah, that's it. But this load will give us movement. Look at this. You will get a movement like this. So P load will act like this, and this P load times the distance will create another moment. We call that P delta effect. P times this delta, that's the deflection. P delta effect will create more moment. So when you have more displacement, this P delta effect is more critical. So K factor, P critical, P delta effect, are all of them are related to each other. So we cannot separate them. So when you will get this greater than 0.005, it means that you have more displacement. So you have K greater than 1, and you will get P delta effect on your columns. We will learn all this stuff. Yeah, P delta effect. Next week, I'm going after this one, and you will learn how to calculate P delta effect on your columns. But right now, these are just a start to understanding all this stuff. When you have more movement, the P delta effect is more critical on your column than if you have a small displacement. You have a frame like this one, and the displacement is too small. Yeah. So P delta effect, as you can see on this one, is much less than the other one. Is that clear for you guys? P delta effect, P times this delta will create moment. P times distance will create moment. New moment will add to this column that had already a moment caused by the loading, vertical loading and horizontal loading. Then this P delta effect will add to those. Is that clear?
Yeah, that's clear.
Yes.
Okay, so please let me know if you have any question on this one to make this completely clear before we go to the actually next class.
I also had one more question. So for
Sure.
the shear US, is that both F1 and F2? Or is that just only F1?
Look at this. For this story, above That's it. Always that's the case. Shear is all the forces above. That's it. So you have V F1. For this case, if you are checking this story, your VUS is F1 plus F2, all the forces above. Yeah, that's the rule. All the forces above. So it can make it easier to not to forget any forces.
Okay, thank you.
Welcome. Any other question? Okay, so I think you got it. And please just remember, right now is in your short memory. I'm repeat this because it's important. If you are not reviewing this very soon, if I was you, I'm doing that tonight. Yeah, review this chapter. As you can see, it's not that a long chapter. It's very easy to understand and read this one more time to make sure that you got it. Okay. And another stuff that we need that for next week is actually for moment of inertia for the crack section. Yeah, for the crack section, you should go for the beams. As you saw, we calculated, we did a lot of calculations for the crack section to find IE. So it's hard. Can we do that here for column design or these factors? No, it's very hard. In order to find the K factor, we have to find moment of inertia, crack moment of inertia for the beams and columns. How can we do that? Should we go to that? No, there is no need for that. Just follow these instructions for this on this sheet and you can cover everything. For the beams, consider 35% of IG. IG, what's that? B and H with no crack. You don't need to consider any rebar. IG. BH3 divided by 12. And for the columns, and 35% of that for cracked beam cross-sectional, I crack for the beam, 0.35. But if you have a rectangular, that's BWH or 3 divided. For T section, just remember, for T section, go with this twice as if you have a slab with rebar that is poured with the beam and the rebar of the beam will go to the slab. So in this case, we call that T section. In this case, IG for the beam go 2 times BW times H in the power 3 divided by 12. Okay, this double of that. So if you have T section, your beam should be 35% of this. 35 times 2 means 70% of BWH means IG. So for regular rectangular beam, 35 IG. For T section I beams, 70% of IG because IG is the same as rectangular. Just double of that, 2 times 0.35 means 0.75, 0.70. Please just remember. I will repeat that again during some examples next week. But just remember this. Regular beam, 35%, right, rectangular. T section beam, double of this. For the column, why I crack for the column is less than beam? This is my question. Why for the beam we consider 35%, for the column 70%? Why? Any answer on this?
Can you give us a moment?
Because what? What was your answer? Maybe that's a right answer. Please repeat that. What was the answer?
Can you give us a moment, please?
Okay, sure.
Can you repeat the question one more time?
The question, look at this. That's the moment of inertia cracked section. For the beams, consider 35% of IG. For columns, consider 70% of IG. Why? Why for the columns we can get bigger size for crack? Yeah, it's almost 30% less of IG. That one is 65% of IG. Why? Why for columns, crack section, moment of inertia of crack section is much bigger than the beams. It's almost double of the beam. Why?
Is it because it's more axial?
I think you gave the right answer. Can you just describe a little more why axial is will give us less crack?
Your most likely your moment's probably not going to be as crazy in the column versus the beam because the loading's axial compared to the beam.
Perfect. That's the correct answer. Very good. Yes, because when imagine if the column is completely under compression and there is no moment on the column, so there is no crack on the column. But beam is always under moment. There is no beam with no moment, yeah, because otherwise it's not a beam. So beam will get a lot of bending moment. So you have tension and compression. In column, because the main actually things that the column should do is transferring the axial load, axial compression load. So it can cover a lot of cracks if it can carry a small moment relative to the axial load. So you will not get that much actually that much crack. So because of that, the crack moment of inertia of the crack section is much bigger than the